Okay, we're back to talk nutrient cycling. And first of all, we're going to talk about the water cycle. So, as always, share my screen with you guys. Okay, so I think most of you guys are generally probably familiar with the idea of the water cycle, the fact that the same molecules of water move around and around and around. And sometimes those water molecules are broken apart through things like photosynthesis, and then they're put back together through things like respiration. But generally, the same basic components that make up the water today were making up the water in the past, and they've just been moving around and around and around. So a fancier word for the water cycle is the hydrologic cycle. So hydro is just like the root word for water. And basically, when people talk about the hydrologic cycle, what they mean is the model that we use to account for the movement of water on the planet. So water can move through evaporation from a liquid form to a gaseous form in the atmosphere. It can move through condensation. It can move through precipitation. It can move through percolation through the soil. And so even a kind of complex diagram like this that shows lots of different pathways for water, in reality is a bit of an oversimplification for how many different places water can go and how water can move. But again, it's a conceptual model that helps us understand how water is moving around in different reservoirs or locations where it might be stored, which doesn't just only mean like a lake, or which we think of as a reservoir, but can be stored in living organisms. That's a potential reservoir. Glaciers are a potential reservoir. Soil is a potential reservoir, etc. And unlike other nutrients, water in the water cycle constantly stays as the same compound. So as carbon moves around, as nitrogen moves around, it is experiencing chemical reactions that is transforming carbon from like carbon dioxide into glucose, et cetera, et cetera. So it's changing through chemical reactions. The water molecule does experience chemical reactions and can be broken apart and remade. But when we think about the water cycle, usually we're thinking about those water molecules that stay together. And then we think about how that molecule as a whole is moving from one place to another. And usually it moves as it changes what we call its phase. So as it goes from a liquid to a gas, or a gas to a solid, or a solid to a liquid. So like melting ice or evaporating water or snow falling. So in all those cases, it's changing its phase. And that is one of the drivers that's moving the position where it is and moving it from one reservoir to another. So far and away, most of us are probably familiar that most of our water is in the oceans. The oceans cover about 73% of the Earth's surface, but they contain almost 98% of the water, and that's because the oceans are very deep. So sometimes our planet is referred to as the blue marble, and we look at pictures of the planet from space. A lot of it's covered with this blue ocean. And when we talk about different reservoirs of places where water may exist for periods of time, we also talk about another concept which is called residence time, which is how long the average water molecule that enters that particular reservoir will stay there. So some can move through very fast. A molecule of water might fall down as a raindrop and then evaporate right away off the surface of the ocean. So it might have a very short residence time. Other water molecules might be trapped in the very, very deep ocean away from currents for long periods of time. But on average, a water molecule that enters the ocean stays there for about 3,000 years, which is a relatively long residence time compared to the scale of a lot of nutrient cycling. Okay, so fresh water makes up a much smaller portion of the water, about only 2 or 3% of the water on the planet, but that is the water that most terrestrial organisms are primarily dependent on. So in terrestrial ecosystems, what's going on with the ocean is not nearly as important as what's going on with the fresh water. So of the fresh water, the largest reservoir by far is glaciers and ice caps. They make up about 77 or 78% of the water that exists is frozen. And again, sometimes water freezes like a snowflake and then evaporates away very, very quickly within one day. but residence times can also last many hundreds of thousands of years. So we have ice that has existed in glaciers for long periods of time. And in general, that residence time is going to be a lot longer than some of these other that we'll mention. The next biggest reservoir is groundwater. So that's not just water that's on the surface of the soil, but water that's stored deeper down and kind of longer term, what we call aquifers. And we'll talk more about those later. So water that goes down into an aquifer is more likely to stay on the scale of like hundreds of thousands of years. And then all these other systems are more surface water systems. So like lakes, soil moisture, then the atmosphere, rivers, and biological organisms. In all these cases, first of all, the percentage of the amount of total water that's stored in all these systems is very small. So if we add all of them up, it's still less than 1% of all the fresh water on the planet, which is, of course, a really small percentage of all the water on the planet if we think how much is in the ocean. And so you can think about how it's not surprising that water is a limiting component. Remember, we talked about Liebig's or Liebig's law of the minimum, and lots of ecosystems because there's not that much fresh water to go around. And it also moves quickly. So the residence times are short, like years to weeks to months, moving in and out of an organism, in and out of a river, in and out of the soil. So as we said a couple slides ago, one of the main ways that water moves is by changes to its phase, moving between a liquid, solid, and a gas. And that transformation is primarily driven by differences in temperature, right? As heat is absorbed, temperatures increase. As heat is lost, temperatures decrease. And so we can evaporate water, turn it from a liquid to a gas. We can condense water, turn it from a gas back to a liquid. Precipitation is the movement of a liquid or solid form of water from the atmosphere down to the ground. We can melt snow and melt ice, moving from a solid form to a liquid form. So all of these are kind of different ways that water is being transported around. And in many cases, they're being driven, again, by these differences in temperature. So in all of these examples, we'll think a little bit about some of the influences that humans have had on these basic kind of systems that transfer these nutrients, in this case, water, around in the environment. And so one of the main changes that we have seen over the last 100 or so years is a change to the average temperature of the globe. So on the last slide, we said the temperature of an environment is so important in determining how water is moving and where water is going to exist and reside. So if we're changing the temperature of the environment, we're going to be drastically changing the water cycle. And so first of all, we may have higher rates of evaporation. So we might have less soil moisture, less water available for vegetation growth. We might have more water vapor in the atmosphere that can lead to intense storms and things like hurricanes. And then of course, one of the classic kind of very well documented, well-known influences of this warming climate is the melting of the ice cap. So if it's warmer, we're melting ice caps really significantly. And so we're transferring a lot of water from that reservoir that we talked about in ice and glacier and turning it into liquid water in the oceans and other places. And that's leading to things like sea level rise, which we'll talk a lot more about later in the class. So this is a little animation, and unfortunately it's not showing up right now, but it's showing the change in the dimensions of the polar ice cap, so up by the North Pole, today compared to 20 years ago. And I'll link it up so you guys can look at this animation through Canvas, but it's a lot smaller today, unsurprising. I think nobody would be surprised to hear that. Okay, I think that's the end of our water cycle. So we'll come back